Hi everybody, I'm going to talk a little bit about how to determine orbital function today in this video. So we're going to be thinking about, what orbitals are on an atom and what are those orbitals exactly doing? Are they making bonds? Are they holding lone pairs? What kind of bonds are they making? That's kind of the thing that we want to be thinking about today. And this is really going to help us kind of get a better idea of, how reactions occur and, what's going on with those bonds to make those reactions or break those bonds or form new bonds, whatever. So the first step you want to think about is you really need to determine the hybridization of the atom first. So think about what hybridization it is, because as we know, that hybridization is going to tell you what orbitals are present on that atom. So if it's sp3, you're going to have 4 sp3. If it's sp2, you're going to have 3 sp2 and 1 p orbital. And so on. So if you have not yet gotten comfortable with that, I would recommend going and looking at that hybridization video again, so that we know, okay, what orbitals do we actually have present here? So then we list out the orbitals that are present. Then we make another list of what bonds we have to that other atom, to any other atom, and what lone pairs are present. So if it's an oxygen, does it have 2 lone pairs and 2 bonds? If it's, does it have a pi bond on it? We would want to know what kind of bonds and if we have lone pairs present. And then both of these things, if you're doing it right, you should have 4 things here. And you should have 4 functions. So each of those orbitals gets a function, okay? So you should just be able to match 2 and 3 together, and that's your step 4. Okay, match the orbitals to the bond or the lone pair that they're making, and that's going to be the function that they hold. So pretty much what we have as options here, and what we want to remember is remembering that sigma bonds are always going to be made of hybridized orbitals. So that's going to be your sp3, your sp2, your sp. So we're looking at this stuff. And a pi bond is always going to be made of p orbitals, okay? So those two are kind of set in stone. The one that's a little bit wishy-washy is our lone pairs, okay? They can actually be in hybridized orbitals if they are localized, or they can be in p orbitals if they are delocalized. So that's something that we're going to have to take a little bit of a look at to kind of see which one is localized, which one is delocalized, and what does that mean in terms of what orbital that lone pair is in. So let's look at an example. That's going to be the best way to go through this and figure this out. So for each of these, I have a few atoms labeled here on this molecule. So I've got A, B, C, D, E, and F. So these atoms are what we're going to be looking at to fill in this table. So we're looking at bond angle, geometry, hybridization, orbitals present, and what that orbital is doing, the orbital function, okay? So when I'm looking at this, I tend to think that the hybridization is the easier one to start with, because that helps you fill in kind of the rest of this. Because it's kind of tough to tell bond angle when you're just looking at it and you haven't thought about the hybridization, because bond angle, geometry, hybridization, those all kind of go together. So let's go ahead and start with A. I'm going to draw out our H's here. I always think that when you're doing hybridization, it really helps to see everything that's around. And in that, just in terms of that, let's go ahead and draw in all the lone pairs on our oxygens as well. So on oxygen B, we've got 2 bonds. So that's a total of 4 electrons in that bond, in those 2 bonds. So to get to 8, I need another 4 electrons. So that's going to be 2 lone pairs on oxygen B. I'm going to have a very similar situation on oxygen D, where I've got 2 bonds. So I need 2 lone pairs to get to 8, and E as well. Okay, so I have all my lone pairs in. Let's go ahead and start with A. So A, I've got 1, 2, 3, 4 atoms attached to carbon A. So that immediately is going to put me in an sp3 hybridization state. Okay, sp3, that means we're going to have a tetrahedral geometry. And that means that our bond angle is going to be that 109.5. And for that, if you can just remember 109 or maybe even 110, that's totally fine. Approximate is not a big deal here. But we're really looking at kind of, this is the farthest away that you can put 4 things in space in a 3D space. Okay, that's what the tetrahedral geometry is giving you. It's giving you kind of keeping things as far apart as possible. Okay, so then we go to orbitals present. sp3 atoms always have the same orbitals present on them, and that is 4 sp3 orbitals. Okay, so then we basically have to figure out what exactly do we have going on this atom. So this carbon atom, we've got a sigma bond to an H, another sigma bond to H, and a third, and then we've got a sigma bond to a C. Okay, so all of these single bonds are all of our sigmas. So with sp3, it's actually pretty easy to assign the function, because all you need to do is really list out like all the stuff that are on that one atom, because you don't have any choices here besides sp3, right? So there's nothing for us to pick between. So we've got a sigma bond to H, and then a sigma bond to C. Okay, so then we're finished with A. So let's go ahead and take a look at B. So for B, first thing we want to do is assign hybridization. So we count the things that are around it. So we're counting atoms and lone pairs. So 1, 2, 3. So this is going to be an sp2 oxygen. Okay. That means that my geometry is going to be that trigonal planar. Okay, so it's pretty flat. For bond angle for this one doesn't really make a whole lot of sense to do, just because we only have angles between lone pairs and atoms, not actual bonds between them. So we'd be looking at a bond here, but since we don't have a bond there, that bond angle doesn't really make a lot of sense. Okay, so for orbitals present, every sp2 atom has 3 sp2 orbitals and 1 p orbital. And remember, keep in mind that we're looking for kind of the magic number of 4 here, where this should always be 4 orbitals in a list. Okay, 4, 4, it's always going to be that. So then if I'm looking at this oxygen, I have a few more things happening here. So I'm just going to kind of list out some stuff, and then we'll go ahead and rearrange it. So if I'm looking at our oxygen, I've got 2 lone pairs. So I've got 2 sets of lone pairs. I've got a sigma to C, and that's taking care of one of these lines. But then what makes it a double bond is that I have a pi bond there. So I also have a pi bond to C, okay? So this, I've just kind of like written this up. I'm actually just gonna, oops. Okay, we'll put it up there and then we'll just drag them down as we talk about them. Okay, so one thing to keep in mind here is if I have a pi bond, I know that there's only one orbital that can make a pi bond, and that is the p orbital. So then automatically, I know just kind of by process of elimination, and I tend to start with the p orbitals. If I've got a pi bond that I'm looking at it, I tend to start there just so that then, you know, this becomes a much easier decision when you have 3 things left over. Okay, so you've got a p giving you your pi bond to C, so giving you your double bond. And then we can basically just put the rest of these in here, because the only orbitals we have left are sp2. We don't have any other p orbitals to mess around with. And if you're thinking about resonance, right, if we're trying to delocalize that lone pair or the other lone pair, it doesn't matter which one, right? If we try to do this, we've created a bunch of problems here. So if we look at this carbon, that's way too many electrons for that carbon there. Okay, so right now it's got 2, 4, 6, 8, 10 electrons on it. So we've broken the octet rule there. So that is not a valid resonance structure. meaning that these two lone pairs are localized. Okay, so we're just going to make a note. Okay, those are going to be on our sp2 orbitals. All right, so let's go ahead and look at C. So again, I'm going to draw out the H on C so that we just have everything in one place in front of us. So then we're going to count all of the things around it. So lone pairs and atoms. 1, 2, 3. So this one is another sp2 atom. So again, we're going to have a trigonal planar situation. In this case, I do have actual bond angles that I can be looking at. Those are 120 degrees. Okay, anything that's sp2, we can kind of consider it falling into that, that trigonal planar geometry there. All right, so then orbitals present. We know that one because it's going to be the same for every sp2 atom. Then we need to make our list of what we have going on here. So on this carbon, we've got a sigma bond to an H. We've got a sigma bond to C, so that would be this one here. We have another sigma bond to the other carbon. And then to make that a pi bond, we've got a pi bond to that carbon as well. Okay, so we've got 3 sigma bonds, 1 pi bond. So again, let's go ahead and start with the easy one. So we do have a p orbital. So that pi bond is going to be made from that p orbital, which means that all the other stuff ends up getting in those sp2 orbitals. All right, let's look at D. So D, I've got 1, 2, 3, 4 things. Okay, D though is particularly tricky. The reason that it's tricky is because we always want to keep an eye out for lone pairs, right? We looked at the lone pairs over here and decided there's really nothing else that they can do. They are localized on that. We have no options in terms of resonance over here, but we can, let's do it in purple here. We can use our lone pair next to pi bond resonance pattern. Okay, back from that brief interruption. So we have the lone pair next to pi bond resonance pattern, and I'm not going to draw all of it. I'm just going to draw a little portion, just enough so that we can get the idea here. Okay, so we've got something that looks like this. So if I'm comparing what this oxygen looks like over here versus what it looks like over here, right? If I was assigning hybridization in this state, I would say 1, 2, 3, 4 things around it, sp3. But if I'm over here, I'm looking more 1, 2, 3, and now it looks sp2, right? Because now I have something that looks like a pi bond here. So if I have it as sp3 hybridized, that means I'm basically saying I have no resonance possibility here and that I can't do this. But if I can do this, if this is reasonable, which it is reasonable, then that means that that lone pair has to be in something that can do resonance. So it has to be in a p orbital, essentially. So if we're making our list of what we have going on this oxygen, we've got 2 lone pairs. We've got a sigma bond to C and another sigma bond to C. Okay, so one of these lone pairs can be delocalized into that benzene ring like I did over here in the purple. So in order to do that, that means that that lone pair essentially became a pi bond. And what do we make pi bonds out of? P orbitals. Okay, so that means that when we go ahead and put our stuff in here, oh, I've like really skipped some stuff. Oh, that's why. Yeah, we're just gonna catch up on this table. So that means we need to do a little bit of shuffling here. Okay, so that has one of our lone pairs in that p orbital, so that this lone pair is delocalized. But if you think about going from here, is it really possible for the other lone pair to be delocalized? Not really, because then we'd be running into that same issue of kind of overloading that octet over here. So keep that in mind. Usually, if you've got lone pairs, only one of them is going to be able to delocalize if there are multiple lone pairs. All right, so then we've got our geometry and our bond angle. So because it's sp2, it's definitely going to be leaning more on that trigonal planar side with 120-degree bond angles. And this is one where, you know, it might be slightly smaller than that because it might have a little bit of that kind of tetrahedral character to it. Because as we know, the real structure is kind of somewhere in between these two. But it's not, I would say we're not going to really get too fussy about that. And we're just going to kind of focus on, like, if it's sp2, we're going to consider it to be that trigonal planar 120. All right, so then we're on to E. So for E, I've got 1, 2, 3, 4 things. Again, I'm going to do a really good double check to make sure that these lone pairs can't do anything suspicious on me. So this carbon is sp3. This carbon is sp3 because I've got the two H's. So these lone pairs have nowhere to go. They are definitely localized lone pairs. So let's go ahead and add a note here. This one is delocalized. These two are localized. Alrighty, so if it's localized, then I've got 4 things. So this is going to be another sp3, which means I've got another of my easy ones. Because I don't have to pick anything, I just have to list out the 4 things. So there were 2 lone pairs on that oxygen, and there were 2 sigma bonds to carbons. Okay, that means I've got tetrahedral geometry with 109.5 degree bond angle. All right, then on to F. So for F, we want to keep in mind there is a C right here. Okay, that carbon currently has 1, 2, 3 bonds on it, meaning that it's got an implied hydrogen on it as well. So once we're all drawn out, then we can say we're attached to 2 things. So we're going to have an sp hybridization here, meaning that we're going to have 2 sp orbitals, 2 p orbitals, still a total of 4 orbitals. All right, so then we've got 1 sigma bond, 2 pi bonds, and then a sigma bond to H. Okay, so as soon as I've got 2 pi bonds, that's where my 2 p orbitals are going to go. So they're going to be responsible for making those 2 pi bonds. And then we've got a sigma to H and a sigma to the C. Okay, for sp, that's going to be a linear geometry. With a bond angle of 180 degrees. So this is one we want to be really careful when we're drawing it, that we keep that bond angle as just a straight line. So we're not going to draw any triple bonds like that. That is incorrect. Okay. And just a little note here for E, where we had assigned it as a tetrahedral geometry. I think your book might have it listed as bent. It doesn't really, I don't really care which one you go with. If you just go with tetrahedral, that's totally fine. Bent is just a couple degrees off of 109. I think it's like 107 or something like that. Just because these lone pairs act slightly differently than an atom, but it's pretty close. So I'm fine with it if you just estimate. Alrighty, so now let's figure out what orbitals make a bond. So for this, our kind of strategy here is we want to determine the hybridization of both atoms in the bond. Okay, so that's first step. Determine the type of bonds. So do you have a sigma, a pi, both? What's going on there? And then we want to keep in mind that the sigma bonds are made of one hybrid orbital. The pi bonds are made of one p orbital, and that's from each atom of that shared bond, right? So either it's two hybridized orbitals coming together or it's two p orbitals coming together, but it's one from each atom to make that bond. All right, so if we're looking at one, so for one, we've got one carbon that's, let's see if I can, we've got this carbon, which we had already decided was sp3, okay, because I've got the 3 hydrogens on it. And then this carbon has 1, 2, 3 things on it, so that's going to be sp2. So for one, that's going to be an sp3 to sp2 overlap, because this is a sigma bond. Okay, so it's made by hybridized orbitals. The only hybridized orbitals present on an sp3 and an sp2 atom respectively are sp3 and sp2 orbitals. Okay, all right, so let's look at 2. So for 2, we're looking at this carbon, which is sp2, because we've got 1, 2, 3. On this oxygen, we had decided up on the first example that this is also sp2, because you've got those lone pairs that can delocalize. So that means for 2, again, I've got a sigma bond here. I've just got a single bond. So that means I've got an sp2 to sp2 bond shown. Okay, I would say kind of not shown is that partial pi bond, but in a question like this, just leaving it as the one that I drew out is totally fine. All right. So for 3, this carbon is sp3. We decided this oxygen is also sp3. So that means that, again, we've got a single bond connecting them between the carbon and the oxygen. So that's going to be sigma bond made of hybridized orbitals. And the hybridized orbitals that we have available to us are sp3 and sp3. Okay, so it's really nice if you're just doing sigma bonds. It's whatever hybridization, that's your hybridized orbital, right? That's the only option that you have for hybridized orbitals. All right, for number 4, so this carbon is sp3. We've got those 2 implied hydrogens. This carbon has no implied hydrogens, and it's got only 2 things around it, so that's going to be sp. And bond 4 is another sigma bond, so that's going to be an sp3 to sp. And then on to 5. Now we've got a bunch more things happening, right? So on 5, we've got 2 pi bonds and 1 sigma bond. So we've got sp over here. So if we're looking at our sigma bond first, that sigma bond is made out of sp and sp orbitals, 1 from each. The pi bonds are only made of 1 orbital type, the p orbital. So that's a p and a p orbital combining together to make that pi bond. And then our second pi bond is going to be the same thing. Okay, so pi bonds always made by p orbitals, sigma bonds always made by hybridized orbitals. Alrighty, so as always, let me know if you have any questions, and we will keep on practicing this.